Science of the planets. The Hubble Space Telescope has observed stars and planetary systems in formation, examined the atmospheres of planets around distant stars, and seen the destructive power of cosmic impacts. What happens on the surfaces of our nearest neighbors? Are there other places with populations that wonder at the skies as we do? As we gather more information about planets and discover new ones, our understanding of planet science expands. Having only 9 worlds on our initial list, including Kuiper Belt object Pluto, is an insignificant sample from which to draw conclusions. The discovery of extrasolar planets, planets beyond our solar system, has stunned astronomers with the wide variety of planetary systems. Giant planets orbiting close to their home stars, planets in strange elongated orbits, even a planet that orbits 2 stars at the same time. Seeing planets within our solar system and beyond enables us to learn more about how these bodies came to be and our own planet. The birth of stars and planets. When clouds of gas and dust collapse, gravity pulls the materials together into a dense object surrounded by a spinning disk of leftover matter. It eventually erupts with jets of intense radiation trillions of miles long, traveling at 500,000 miles per hour, 800,000 kilometers per hour. Scientists are uncertain exactly how the jets form, but believe they result from magnetic fields rotating around the forming star. Astronomers could see jets before Hubble, but not star-forming disks. Hubble's vision enabled them to see both. It captured the first detailed images of jets and disks in the Orion Nebula in 1995. In the past decade, Hubble has taken many images of jets and found the first direct evidence that they originate at the center of the dusty gaseous disk from which the forming star is drawing its raw material. During star formation, the jets are thought to slow down the spinning disk so that more matter can accumulate on the star. The Orion Nebula in a panoramic view. The nebula contains 700 young stars in various stages of formation within a cavern of gas and dust. Astronomers once thought it would be impossible to observe protoplanetary disks, the disk of dust around stars that coalesce into solar systems. The disks were engulfed in giant clouds of gas and dust, making them difficult to discern. By identifying the dark clots of dense dust against the bright background of glowing nebulae, Hubble disproved this theory and found numerous protoplanetary disks. According to Hubble's observations, planet formation is influenced by the environment in which a star develops. The Hubble observations have also provided clues about the missing steps in our understanding of planet formation, such as how a disk of gas and dust evolves into individual planets that orbit newborn stars. Planets outside our solar system. Exoplanet HD 189733b's evaporating atmosphere. Many extrasolar planets have been discovered beyond our solar system. Ground-based telescopes have found most of them by looking for tiny wobbles in a star's motion caused by planets tugging at it or the slight dimming of light caused by a planet passing in front of its parent star. Hubble can provide insights into the planets that cause these light-blocking periods called transits. In addition, Hubble measures the amount of light passing through the atmosphere of the Earth, which allows it to determine the makeup of the atmosphere. Hubble has discovered atmospheres containing sodium, carbon, and oxygen, and a world with a comet-like tail of hydrogen evaporating into space. In addition, the team detected the first organic molecule on an extrasolar planet. Methane in the atmosphere of a Jupiter-sized planet blisteringly close to its star. Space Telescope's ability to make these observations was a breakthrough, confirming and bolstering the idea that they could examine the atmosphere of far-flung planets and set the stage for current and future telescopes to continue this critical science. Moreover, Hubble took the first visible light picture, something astronomers thought was impossible. Observations of Fomalhaut's dusty surroundings had led astronomers to suspect that the star might have planets since the early 1980s. An image of the dust belt around a star shows a tiny speck of Fomalhaut b, a planet approximately 3 times the size of Jupiter that might be surrounded by a disk of dust and gas. Observations of the planet Fomalhaut by Hubble. Scientists used coronagraphs to black out nearby light sources, including the star in the center of the image, to observe the much dimmer planet as it passes near a dust ring surrounding the star. Photographs taken years apart show the planet moving along its expected path. For the first time, Hubble observes a planet orbiting another star. Having suspected for years that planets may exist in other solar systems in the universe, the Hubble Space Telescope captures visible light images that provide the first evidence of these extrasolar planets. Scientists describe the discovery of Fomalhaut b, the first extrasolar planet captured on a camera in visible light. Techniques for finding planets. Planets are microscopic compared to other objects in the universe. Moreover, they can be 1 billion times fainter than the stars they orbit. Astronomers have developed innovative methods to hunt planets in other solar systems since they are nearly impossible to see directly. Transit-based hunting. When a planet passes in front of its parent star, it will cause the star to dim slightly as they block some of the light. Astrophysicists watch for these telltale changes in brightness. Radial velocity hunting. The gravitational pull of a planet causes its star to wobble. Telescopes can detect this wobble by observing the starlight broken into a spectrum of colors. As the star wobbles, dark lines appear caused by light being absorbed by its atmosphere. Astrometry as a method of hunting. A planet's gravity pulls its parent star out of place as it orbits. There is a possibility that a world is pulling on the star if it sways in a periodic rhythm. A telescope with exceptionally sharp vision can sometimes see the star moving back and forth in the sky. Using direct imaging for hunting. Because the stars are so bright and the planets so dim, it's challenging to capture a candid image of an extrasolar world. A mask called a coronagraph can sometimes block enough of the star's light to pick up a planet's dimmer reflected light. Microlensing by gravitational force. Whenever one celestial object passes in front of another, its gravity can bend and magnify the light behind it, making it appear brighter. The closer star will brighten twice if it has a planet. Comet crashes into the solar system. Comet Shoemaker-Levy 9 plunged into Jupiter's atmosphere in 1994, sending large plumes of debris into space. A spectacular view of the event was provided by Hubble, who watched the comet approach the collision site. As Jupiter's gravity shattered the comet into dozens of fragments, it observed violent waves erupting from the impact sites. Scientists believed it was a once-in-a-thousand-years event. Astronauts visited Hubble in May 2009 to install new instruments. In July, an amateur astronomer discovered a strange dark spot on Jupiter's surface as engineers and scientists tested and adjusted the refurbished telescope. As a result of an unnoticed asteroid impact, an expanding impact site has been left behind. Once again, the big world has been hit. 1994. First strike. The first comet, P. Shoemaker-Levy 9, which fragmented upon impact with Jupiter, produced a plume near Jupiter's limb. It was an important event that couldn't be missed. Hubble's team temporarily rearranged its schedule to take pictures of the impact site with one of its new instruments. Impacts of comets in visible and ultraviolet light. An asteroid struck Jupiter in July 2009, leaving a bruise the size of the Pacific Ocean. The Hubble Space Telescope observes different forms of light, allowing us to see more detail than we might otherwise. After a recent servicing mission, engineers interrupted the telescope's calibration to take a picture of the impact. As seen in visible light, Jupiter shows impact sites in its southern hemisphere. The same places on the planet are visible in an ultraviolet picture taken 20 minutes later. This image shows the comet's residue and materials thrown from Jupiter's lower atmosphere into its upper atmosphere by the impact, since the fine particles are easier to see in ultraviolet light. The images were taken on July 17, 1994. Images of Jupiter's impact sites raise questions about the planet's composition. The properties of the waves racing outward from Shoemaker-Levy 9 sites, for example, indicate that the planet's design is less similar to the Sun than researchers previously thought. Hubble's advantage is its ability to take high-quality images of such events on short notice, enabling us to deeply study our cosmic neighborhood. Given the short interval between results, one may wonder if these impacts are as rare as once assumed. Perhaps the timing of these incidents is coincidental, or perhaps collisions occur more frequently than we thought. Scientists once thought they had implications in our solar system that occurred thousands of years apart. NASA's Space Telescope. Since the dawn of astronomy, astronomers have shared one goal: to see more, see farther, see deeper. Humanity made one of its most significant advances in that journey thanks to the launch of the Hubble Space Telescope in 1990. The Hubble Space Telescope is one of NASA's most successful and long-lasting science missions. It is located above the atmosphere. It views the universe typically much better than ground-based telescopes. It has relayed hundreds of thousands of images back to Earth, shedding light on many of the great mysteries of astronomy. Named after a legend. Dr. Edwin Powell Hubble, an astronomer who made some of the most important discoveries in modern astronomy, is the name of the Hubble Space Telescope. Working with the most advanced technology at the Mount Wilson Observatory, Hubble showed in the 1920s that some of the numerous distant faint clouds of light in the universe were entire galaxies, much like the Milky Way. It changed the way astronomers viewed our place in the universe forever when they realized that the Milky Way was only one of many galaxies. Hubble's most important discovery came when, in 1929, he discovered that galaxies appear to move away from Earth faster the farther from Earth they are. The Big Bang theory posits that the universe began with a burst of energy at a single point and has been expanding ever since. Hubble Space Telescope cross-section. Hubble travels at about 5 miles per second, 8 kilometers per second, fast enough to cross the country in about 10 minutes during its orbit around Earth. Hubble's mirror captures light as it travels and directs it into its science instruments as it does so. A Cassegrain reflector telescope, such as Hubble, is a type of telescope. The main mirror or primary mirror reflects light. After being reflected by the primary mirror, the light is reflected by a secondary mirror. Using the secondary mirror, light is focused through a hole in the primary mirror, which is connected to the telescope's science instruments. It is a common misconception that the power of a telescope lies in its ability to magnify objects. A telescope works by collecting more light at a higher resolution than the human eye can see. The larger a telescope's mirror, the more light it can hold, and its vision is better. Hubble's primary mirror measures 94.5 inches, 2.4 meters. It is smaller than current ground-based telescopes, measuring 400 inches, 1,050 centimeters, but Hubble's location beyond the atmosphere gives it remarkable clarity. Following the light's capture by the mirror, Hubble's science instruments work together or individually to provide the observations. These instruments probe the universe in different ways. Hubble's functions are all powered by sunlight. Solar panels on Hubble convert sunlight directly into electricity. When the telescope is blocked from the sun's rays, some electricity is stored in batteries in Earth's shadow. Design of the Hubble Space Telescope. Wide Field Camera 3, WFC3, detects near-ultraviolet, visible, and near-infrared light, but not all at once. It is now Hubble's leading and most efficient camera. COS is a spectrograph that sees exclusively in ultraviolet light. Like prisms, spectrographs separate light from the cosmos into their component colors. A wavelength fingerprint provides information about an object's temperature, chemical composition, density, and motion. Advanced Camera for Surveys, ACS, sees the light in wavelengths from the far ultraviolet to near-infrared and is designed to study some of the earliest activity in the universe. ACS identifies the most distant objects in the universe, searches for massive planets, and examines the evolution of galaxies' clusters. NICMOS is Hubble's near-infrared camera and multi-object spectrometer. The Space Telescope Imaging Spectrograph, STIS, is a spectrograph that sees ultraviolet, visible, and near-infrared light and is known for its ability to spot black holes. COS can map out small objects like stars and quasars, but STIS can map out larger objects like galaxies. Working with Hubble's instruments. Hubble's primary camera, WFC3, imaged NGC 6302 in ultraviolet and visible light with various filters to determine the properties of the nebular gas. It can observe objects hidden by interstellar dust, such as stellar birth sites, and peer into the deepest reaches of space using light which humans perceive as heat. Known as Fine Guidance Sensors, FGS, these sensors keep Hubble pointed in the right direction by locking onto guide stars. They can be used to measure stars' positions and motions precisely. Large Space Telescope Concept Art. In 1923, German scientist Hermann Oberth, one of the founders of rocketry, proposed blasting a telescope into space aboard a rocket. Lyman Spitzer Jr., an American astrophysicist, proposed a space observatory in 1946. During the next 50 years, he would devote himself to making this space telescope a reality. In 1969, NASA approved what was then called the Large Space Telescope Project. The original proposal was downsized to stay within budget, reducing the size of the telescope's mirror and the number of instruments it would carry. The team working on the project proposed a telescope with several interchangeable instruments. The telescope would either be returned to Earth for repairs and replacement instruments or serviced in space in orbit. Legends are made of this. Several decades before the Hubble telescope became a reality, legendary scientists considered the possibility of a space observatory. The European Space Agency, ESA, and NASA began working on a plan that eventually became the Hubble Space Telescope in 1975. To supply NASA with manpower and funding, ESA's support was crucial. NASA would provide the solar cells and one of the telescope's instruments, the Faint Object Camera. Congress approved funding for the telescope in 1977, after being reassured by the partnership. NASA centers and companies like Lockheed Missiles and Perkin-Elmer Corporation began working on the Hubble telescope piece by piece. The astronauts trained in a weightlessness tank in 1979 using a mock-up telescope to simulate Hubble Space Telescope construction. Lockheed Missiles and Space Company, Lockheed Martin, diagram of the Hubble Space Telescope. Hubble was scheduled to launch in October 1986. Tragically, the launch was delayed until January the 28th. Just over a minute after liftoff, the Space Shuttle Challenger exploded. Shuttle flights were suspended for 2 years. The telescope parts were stored. During the delay, Hubble workers continued improving solar batteries and upgrading other systems. Hubble was launched into orbit on April the 24th, 1990, aboard Space Shuttle Discovery. 5 instruments were carried by the telescope: the Wide-Field Planetary Camera, the Goddard High-Resolution Spectrograph, the Faint Object Camera, the Faint Object Spectrograph, and the High-Speed Photometer. Designed to be repaired and upgraded by astronauts in orbit, it would be needed sooner than later. Starting off on the wrong foot. It was clear almost immediately that something was wrong after Hubble entered orbit. The pictures were more explicit than those of ground-based telescopes, but they were not the new images promised. The photos were blurry. In Hubble's primary mirror, polished so carefully over an entire year, there was a flaw called spherical aberrations. The mirror was just slightly the wrong shape, which caused the light that bounced off the center of the mirror to focus differently from the light reflecting off the edge. This flaw, about 1/50th the thickness of a sheet of paper, was enough to distort the view. Hubble was the first instrument to come with built-in corrective optics. Scientists and engineers were faced with a well-known problem. Astronomers had been dealing with spherical aberrations since Galileo's time, but Hubble's mirrors could not be altered or replaced while in orbit. Fortunately, a solution was found. Mirrors could be used to intercept the light that reflects off the mirror, correct for the flaw, and bounce it to the telescope's science instruments. COSTAR, or Corrective Optics Space Telescope Axial Replacement, could be installed in place of one of the telescope's other instruments to correct their images. In addition to replacing the Wide-Field Planetary Camera, astronauts will install the Wide-Field and Planetary Camera 2, WFPC-2, containing small mirrors to correct aberrations. As scientists and engineers worked, Hubble sent back images that, despite their flaws, still gave astronomers a better look than they'd previously had at the kind of cosmic phenomena Hubble was intended to reveal. Scientists developed new image processing techniques that partially recovered some of the information lost due to blurring. A planet-spanning storm churned on Saturn. The number of stars in galaxy M87 revealed the scale of the supermassive black hole at its center. The lobes of gas emitted by the unstable, explosive supermassive star Eta Carinae were observed. The science Hubble accomplished with the problematic optics hinted at what could be accomplished with a fixed mirror. One of the most complex space missions was trained for 11 months by astronauts and NASA staff. Over 100 specially designed tools would be used in the repair process. It would be the first test of the telescope's vaunted capability of being serviced and repaired in space and its critical nature. The Space Shuttle Endeavour launched 7 crew members into orbit on December 2, 1993, for a mission that involved 5 days of spacewalks and repairs. The high-speed photometer was replaced with COSTAR. The Wide-Field Planetary Camera 2 replaced the original Wide-Field Planetary Camera. They also replaced solar panels, fuse plugs, and other hardware. They were finished on December 9th. Training for the first servicing mission. The Neutral Buoyancy Simulator simulates weightlessness by filling a vast water-filled tank with water. A view of the Indian Ocean shows the Space Shuttle Endeavour approaching the Hubble Space Telescope. NASA released the first images taken by Hubble's fixed optics on January 13, 1994. The photos were gorgeous, the resolution was excellent. Hubble finally became the telescope that had been promised. Pillars in the Eagle Nebula, M16A, one of Hubble's most famous images. Hubble's 1993 servicing mission was the first of many successful attempts to upgrade the telescope. Hubble received 2 gifts from the Space Shuttle in 1997, 2 instruments that featured technology not available when scientists designed and built the original equipment. New appliances gave Hubble a broader view of the cosmos, a pattern that repeated itself in the years that followed as astronauts brought Hubble improved technology. Astronauts would visit Hubble in 1997, 1999, 2002 and 2009. 3 of Hubble's 6 gyroscopes had failed, and Hubble needed at least 3 to observe a target. In November 1999, a 4th gyroscope failed, forcing Hubble into safe mode. Hubble was protected but could not keep its targets. In December 1999, Servicing Mission 3A was launched, followed 3 years later by Servicing Mission 3B. In 7 months, we developed, approved and executed an urgent call-up mission. In Servicing Mission 3A, astronauts replaced all 6 gyroscopes and installed more powerful electronics, batteries and new insulation. Hubble's Advanced Camera for Surveys, ACS, and a new power control unit was installed for Servicing Mission 3B. It was a delicate mission. Hubble had to be turned off for the first time since its launch to replace the power unit. The mission went well, and ACS, with its wide field of view, superb image quality and exquisite sensitivity, brought 10 times more discovery power than the camera it replaced. An astronaut visit to Hubble in May 2009 was the culmination of a long effort to provide one more servicing mission to the telescope. The mission was initially scheduled for 2004. The view from Hubble improves over time. A Hubble image of a small region of the Orion Nebula reveals how the telescope's vision has improved over time. Hubble's 4th servicing mission was perhaps its most challenging and intense. As a result of the loss of the Space Shuttle Columbia, the mission was postponed until May. NASA approved a second shuttle mission after restarting the shuttle program and re-examining the risks. 2 weeks before the launch of the task in late September 2008, a malfunction occurred in a system that controls science instruments and directs data flow within the telescope. The problem was resolved by switching to a backup plan, but NASA was unwilling to leave the telescope without a spare. ACS and the Space Telescope Imaging Spectrograph, STIS, had already stopped working because of electrical malfunctions in 2007 and 2004. As part of Servicing Mission 4, astronauts installed a replacement data unit and performed on-site repairs for 2 failed instruments that had never been imagined by telescope creators. During spacewalks, astronauts had to crack into the interior of the instruments, replace components, and reroute power. In addition to Hubble's nail-biting repairs, 2 new advanced instruments, the Wide Field Camera 3 (WFC3) and the Cosmic Origin Spectrograph (COS), gave Hubble 5 tools for future observations. Hubble's latest workhorse instrument, WFC3, is susceptible and efficient, and it is capable of taking ultraviolet, optical, and infrared pictures. The COS spectrograph examines nearby stars, distant galaxies, and gas and dust. Space Shuttle Atlantis and the STS-125 crew launched on the final mission to upgrade Hubble on May 11, 2009. At first, NASA hoped Hubble could be brought back to Earth by the end of the task. Since SM-4 is likely to be the last astronaut mission to Hubble, astronauts installed a new device, the soft capture mechanism. In the future, when Hubble reaches the end of its life, a robotic spacecraft could attach itself to this device and guide it through its descent into Earth's atmosphere. Hubble will eventually cease to exist. Over the years, Hubble's components will gradually degrade to the point that the telescope stops functioning. When that happens, Hubble will continue orbiting Earth until its orbit decays, allowing it to spiral toward Earth.
Papa na, Yana, Jai Mama Irina.